So I would like to start off with the idea of having two spin half particles, two protons, two electrons. So my bipartite system now comprises two spin half particles. So I would like, it's a four-dimensional Hilbert space, we all know that. And this four-dimensional Hilbert space is spanned by four basis states. Now we can choose an infinite variety of bases. One possibility is that we choose the states Z, direct product Z, Z, direct product with minus Z, direct product with Z, and minus Z, direct product with minus Z. So this is one possibility for the choice of the basis, correct? Where kept Z's are eigenstates of the SZ operator. So a shorthand notation we all know for writing this is Z, Z. So this can be written as Z, comma Z, or it can also be written as Z, get Z, get Z. So there are different ways of writing the same state. So this forms a natural basis for the four-dimensional Hilbert space. Okay. But this is not the only basis, we all know that. We can also choose some other basis. For example, we can choose the X, minus X, minus X, X, and minus X, minus X. So this is also a basis. We can also choose Z, X, Z, minus X, minus Z, X, minus Z, minus X as our basis. So this is an infinite possibility of bases that we can choose. And the basis that we choose for the Hilbert space is independent of what Hamiltonian we are talking about. So any eigenstate, any quantum state of the two-particle, two-spin half system is a member of a Hilbert space, which is really the direct product of the Hilbert space of the first spin with the Hilbert space of the second spin. Okay. So all of these basis states span the Hilbert space, the joint Hilbert space. Right. We can also have more other kinds of bases. For example, we can choose the four Bell states as the basis states. We can have phi plus, phi minus, psi plus, psi minus as the basis states. There's nothing wrong with that. Any quantum state living in this Hilbert space spanned by the two spin half systems can be decomposed as a superposition of the four Bell states. Okay? Alright, so suppose we choose as our basis, suppose we have this basis state Z, Z. Okay? Now we know that this quantum state lives in a four-dimensional space. Okay? And we also know that if I have, so if I just draw the Hilbert space very schematically, very roughly. What I will obtain is that this is a Hilbert space H1, this is another Hilbert space H2, okay? And the joint Hilbert space comprises both of these Hilbert space, and this state lives in the joint Hilbert space. Okay. Now, if I would like to define an operator S1 X, for example. Now this operator is defined in such a way that it acts only on the Hilbert space of the first spin, on this Hilbert space H1. Okay? And it's a component of the angular momentum operator known the X direction. Alright? So we also know that this angular momentum operator is a generation of rotations. Any rotation that takes place in the first Hilbert space. It has nothing to do with the second Hilbert space. Such a rotation can be written as e raised to the minus I theta S1x over h bar. Correct? So S1x is a generator of rotation in the first Hilbert space. Now this operator acts on a quantum state ket z, which is a joint quantum state. It's a state for the bipartite system. But the operator only acts on the first Hilbert space. So it does not touch the quantum state of the second particle which lives in another Hilbert space. This is what the meaning of the direct product really is. That is, these two Hilbert spaces are disjoint. So this operator will only act on the first spin because you have an S1 here. So when this operator acts on the first spin, what we would get is that this first spin is rotated through an angle theta. Okay? So when it is rotated through an angle theta, what do we get? We get z cosine of theta by 2, okay, plus so cosine theta by 2 identity minus iota sine of theta by 2 minus z, right? Direct product with z. So nothing happens to the second spin half system. Only the first spin half system is rotated through an angle theta by 2 in the Bloch scale. Okay? So the new state will become cosine theta by 2 z comma z minus iota sine theta by 2 minus z comma z. Okay? So this operator acts alone on the first Hilbert space. Likewise, we can define operators that act alone on the second Hilbert space only. Okay? So what this means is that any operator that acts on the first Hilbert space, any component of it, Si alpha, will commute with any component of an operator that acts on the second Hilbert space. This commutator is 0, where alpha, beta can be x, y or z. So this operator acts on the first Hilbert space alone, this operator acts on the second Hilbert space alone. So the first operator, this operator acting on state will not touch the second spin half system. This operator will not touch the first spin half system. Okay, that is, so in other words, if I do a rotation in the first Hilbert space, nothing happens to the second spin. And the meaning of this is that these two spin operators will commute. Which means if I rotate the first spin half system and then later rotate the second spin half system, it's immaterial whether I reverse the order of rotation. Okay? I can rotate the second spin belonging to the second Hilbert space before I rotate the first spin belonging to the first Hilbert space. So the order of rotation is totally immaterial. So operators that act on disjoint Hilbert spaces, distinct Hilbert spaces, mutually commute. Okay? So this is तो ये बात समझ रही है आपको? यानी इसका ये मतलब है कि S1x will commute with S2y. This will be 0. Likewise, S1z commuting with S2x will also be 0, and so on. However, S1x will not, of course, commute with S1y. This will not be 0. This will in fact be minus iota h bar S1z. So these angular momentum operators will satisfy the usual commutation relationships. The key point is that angular momentum operators living in disjoint, acting in disjoint Hilbert spaces, different Hilbert spaces, different particles, which belong to different Hilbert spaces, mutually commute. They are disjoint. Now I would like, with this arsenal, I would like to introduce. Sorry? Sorry?
At the top line. Get C is a product with get C, right? अब फिर उसका आपने क्या डाल के 1 get C equals to double get C.
These are different ways of writing the same thing. इसको आप मूवी लिख सकते हैं, इसको मूवी लिख सकते हैं.
इसको और सिर्फ मुझे वाली थर्ड लाइन में यहाँ पे अब we are doing this kind of first spin half system with Z using Z based parameters and express system.
Measure, this quantum state is irrespective of how you measure. So this is just one particular choice of the basis. So you can write a quantum state without resorting to measurement because the quantum state exists before the measurement. It does not depend upon the measurement. You can measure any of these states using a Stern-Gerlach operators oriented along X, along Y, along Z. It doesn't need to matter. Now I would like to introduce to this arsenal the concept of the hyperfine interaction. So this will reveal most of these concepts that we've learned so far as far as two-spin half particles is concerned. Suppose I have the hydrogen atom in its ground state. What this means that we have a proton and we have an electron. Okay, and we know what the Hamiltonian of this system is. We've studied that in detail. The Hamiltonian of this system, right, is minus h bar square 2m del square, right, minus e square over 4 pi epsilon naught r, right? The potential energy term and the kinetic energy term. Okay, now, so we also figured out what the energies of the electrons have to be. So the energies have to be quantized minus E naught over n squared. Okay, and we also found out the wave function of the spherical harmonic function. But so far in the discussion, which was revolving around the Schrödinger equation, we did not take into account the spins of the electron and the proton. This is a spin half particle and so is the proton. So a spin half particle we already know has a magnetic moment, mu, right, minus g e over 2m angular momentum operator. Okay, so when this is a magnetic moment and so is this. So when we have two tiny dipoles, okay, oriented in some particular direction, these are just like two magnets interacting with one another, and these magnets will have an interaction, which is called the dipolar interaction. Okay, so the dipolar interaction will depend upon the relative magnitudes of these magnetic moments. It will depend upon the relative angles between the magnetic moments. Okay, just like two magnets that are parallel will have a different energy of interaction than the two magnets that are anti-parallel, than the two magnets that are crossed to the okay. Now, or you can also think is that this magnet, which is the proton, has a certain magnetic field at the side of the electron. So this magnetic moment placed inside the magnetic field of the proton will have a certain energy, and vice versa. So how do we model this energy? How do we model this interaction? We model it through the concept of hyperfine interaction. And why do we call it the hyperfine interaction? Because there are the whole range of interactions inside the hydrogen atom. In the ground state, this electron is in the 1s orbit. So its angular momentum is 0. Orbital angular momentum is 0. So it only has a spin angular momentum. Correct? So it's possible that for excited states or for other atoms such as lithium, L is not equal to 0. L could be 1. So the electron can have an orbital angular momentum. So when an electron has an orbital angular momentum as well as a spin angular momentum, the orbital and the spin angular momentum operators can add up to form a new total angular momentum. So that is called the fine interaction. Hyperfine interaction is just the interaction between the spin of a proton and the spin of an electron whose orbital angular momentum is 0. And it's called hyperfine because it's smaller than the fine interactions. So it's a really small effect. We'll see how big is this effect. Okay. So how do we model the interaction? Every interaction is modeled by a Hamiltonian. We know that. So the Hamiltonian for the hyperfine interaction H is given by 2a over h bar square S1 dotted with S2. Now, where does this Hamiltonian come from? This Hamiltonian comes from electromagnetism. But this is beyond the scope of this lecture for the moment. So we have to take this Hamiltonian for granted. What this tells us is that spin S1, which belongs to the proton, say, and spin S2, which belongs to the electron, and both of them are spin half particles, are interacting. Okay? So when they are interacting, there is a Hamiltonian that describes the interaction, and that this is just a dot product between S1 and S2. Okay? And there is a constant A. Now we have this factor h bar square here because we would like this A to have dimensions of energy. Okay, S1 over h bar. S1 over h bar is dimensionless. Okay, because S1 has h bar subsumed into it. So S1 over h bar is dimensionless, S2 over h bar is dimensionless. So this is dimensionless. A must have dimensions of energy because Hamiltonian is 3 dimensions of energy. So this A has dimensions of energy in joules. Okay. In other words, what this would mean is that if the two angular momentum operators, the spin angular momentum operators were totally aligned, okay, if they were totally perfectly aligned, that is, the two magnetic moments were in the same direction, then the energy of interaction E would be 2a h bar squared S1 dotted with S2. We would simply take ms1 ms2, which is the magnetic quantum numbers, the projection of these angular momentum operators along the z-axis. So we define the angle of orientation to be the z-axis. We can define it to be any axis. So this is ms1 into ms2. This is half. This is half. Okay. And there is also an h bar square here. Okay. So this h bar square is okay. So this is what the Hamiltonian basically means. Now what we are interested in is that this is the interaction between the two spin half particles. We would like to calculate the eigenstates and the eigenvalues of this Hamiltonian. That is, we leave the electron and the proton in the ground state. What energies can the system have? Okay, so we need to diagonalize this Hamiltonian and need to find its eigenstates and eigenvalues. Now this is again a four-dimensional Hilbert space because we are dealing with two spin half systems. So the basis states that we can use are any of these states. Okay? And some of these basis states will be eigenstates of this Hamiltonian, but others will not be eigenstates of this Hamiltonian. Being a basis state of a Hilbert space has nothing to do with the Hamiltonian. There could be certain basis states which are eigenstates of the Hamiltonian, and when the Hamiltonian is written in those basis states, it will be diagonal. Correct? Okay. Now we would like to find the eigenstates and eigenvalues of this Hamiltonian. So let's focus on this hyperfine interaction term. So the Hamiltonian is 2a over h bar squared S1 dotted with S2, which really means S1x, S2x, plus S1y, S2y, plus S1z, S2z. Okay? So S1Z S2Z plus 2 times S1X S2X plus 2 times S1Y S2Y. Okay. Now what I would like to do is that I would like to
for example 1y 2z
the dot product.
so
S1 dot with S2 आपको dot में तो ये like terms हैं. Now what I would like to do is I would like to write S1 plus, which is a raising operator acting only in the first Hilbert space. This is really Sx plus iota Sy, and S1 minus is iota S1y. Likewise, S2 plus minus is S2x plus minus iota S2y. Now if I look at this term, this term can actually be replaced, all of this, by S1 plus S2 minus plus S1 minus S2 plus. This is something that you can work out on your own. Okay? So this term in the Hamiltonian, these two terms are generally called the flip-flop terms. Flip-flop because on the first Hilbert space, the operator is raising the quantum number, and in the second Hilbert space, it's lowering. In the first Hilbert space, if it's lowering, in the second Hilbert space, it's raising the quantum number, the appropriate quantum number. So it's generally called a flip-flop term. So we can write the Hamiltonian, the hyperfine interaction, as 2a over h bar squared, a over h bar squared 2 times S1z S2z plus S1 plus S2 minus plus S1 minus S2 plus. So this is our Hamiltonian. Now we would like to diagonalize this Hamiltonian because we want to find the eigenstates and the eigenvalues for the hyperfine interaction. Okay. So if you would like to diagonalize this, it's quite customary to write the Hamiltonian in matrix form or represent it. So if you would like to represent it, we have to choose a basis. So let's choose the basis ket z, ket z, ket z, minus z, ket z, minus z, minus z. Let's choose this basis. Okay, we can do that. Let's label this state as 1, this as 2, this as 3, and this as 4. Okay, so the Hamiltonian will really be a 4 by 4 matrix, and its terms will simply be 1, 1, 1, h, 1, h, 1, h, 1, okay, 2, h, 1, 2, h, 2, 2, h, 3, 2, h, 4, 2, h, 1, 3, h, 2, 3, h, 3, 3, h, 4, 4, h, 1, 2, h, 2, 4, h, 3, 4, h. So this is the Hamiltonian matrix in this basis. So now we have to find out the matrix elements. Okay, given this Hamiltonian. Okay, so let's look at one of these elements. Let's, for example, look at this element. Okay. So this is our state ket 1. I have to find ket T 2 times S1z S2z plus S1 plus S2 minus plus S1 minus S2 plus. All of this acts on Z. Okay. So now, when S1Z acts on Z, it gives me H bar by 2. Okay. Get Z. When S2Z acts on Z, I get again H bar by 2 Z. So I get a factor of half from this term. The inner product of this with this is then 1. Now what this does, this term raises, when this term acts on ket Z, it gives me 0. When this term acts on ket Z, I get 0. So overall I have half here. Okay. So this term is, and of course there is H bar square over 2 as well, because S1Z acts on ket Z to give me H bar over 2. So there is an H bar square over 2. This is H bar square over 2 multiplied by A over H bar square. This is A by 2. Okay. Right? This term will be 0, 0, 0. Okay. I only need to find the top triangular matrix because the Hamiltonian is Hermitian anyway. Okay. This will also be 0. You can work this out yourself. This will be 0. These terms will be non-zero, and so will this. So this term is also A by 2. This is also A by 2. Sorry, this is minus A by 2. This is also minus A by 2. This term is A. If this term is A, this term has to be A as well. A, remember, is a real number because this is how we define that Hamiltonian. A must be a real number because A must have dimensions of the energy. So if you work out this matrix, it's quite straightforward to do so. The Hamiltonian can quite conveniently be written in this form. Hamiltonian is A by 2, 0, 0, 0, 0 minus A by 2, A, 0, 0, A, minus A by 2, 0, A by 2, 0, 0, 0. interested in finding the eigenstates and the eigenvalues. Okay. Now two eigenstates, the eigenstates and eigenvalues, you have to diagonalize this matrix, but by experience and by inspection you can write down the eigenstates and eigenvalues. So what are the eigenstates and eigenvalues? So first of all, what are the eigenstates? A eigenstate relative. Okay, so this is one eigenstate. One eigenstate is 1 0 0 0, which really is ket C ket C. Okay, the another eigenstate is, as Ali mentioned, 0 0 0 1. This state is minus Z minus Z. Okay, and the corresponding eigenvalues. What's the eigenvalue corresponding to this eigenstate?
A of 2,
A by 2. A by 2. Okay. Now we have to focus on this block. Now these elements were easy because in the first row, first column, there is no other element. This is the only element present in the first row and the first column. And this is the only element present in the fourth row and the fourth column. So these form separate subspaces in the Hilbert space. There is nothing that connects the fourth row or the fourth column with anything else, with any other row or column. Okay. Now we have to focus on this block. So finding the diagonalizing this matrix 4 by 4 matrix is reduced to the problem of diagonalizing a 2 by 2 matrix. Now if you look at this block, and if you use your concept of polymatrices, what is this block equal to? You can decompose it into the polymatrices. Its identity and sigma x. So its eigenstates will just be the eigenstates of sigma x. What are those eigenstates? Plus z minus z, plus x and minus x. Okay? Plus x are superpositions of z and minus z. So the eigenstates of this block will simply be 1 over under root 2, 0, 1, 1, 0 and 1 over under root 2, 0, 1, minus 1, 0. Okay? And so this corresponds to 1 over under root 2 ket z plus, ket z minus z plus minus z ket z. Okay, and this corresponds to 1 over under root 2 ket z minus z minus z ket z. Okay, and now we have to find out the eigenvalues. The eigenvalues are not clear. So if I choose this small block matrix minus a by 2, a minus a by 2, and I take the first eigenstate, which is 1 over under root 2. Now I am ignoring these zeros because I reduced the problem to a 2 by 2 matrix. I have 1, 1 here. Let's see what I get. 1 over under root 2 minus a by 2 plus a is a by 2. A minus a by 2 is a by 2. So I get a by 2, 1 over under root 2, 1 over under root 2. So my eigenenergy is a by 2. So the eigenvalue corresponding to this state is also a by 2. So now this is just a sigma x matrix. So if one eigenvalue is a by 2, okay, now we need to find out what this eigenvalue is. Okay, so simply I can take 1 over under root 2 minus a by 2 a minus a by 2 1 minus 1, and we get 1 over under root 2 minus a by 2 minus a is minus 3a by 2. A plus A by 2 is plus 3A by 2. So I get minus 3A by 2, and the origin is 1 over 2 minus 1 over 2. So this eigenvalue is minus 3A by 2. So now I have found out the eigenstates and the eigenvalues corresponding to the hyperfine interaction. Right? I can plot these eigenstates. If this is my datum level for the this is my zero energy level, it's my datum level if I ignore the spin. If I include the spin for the proton and the electron for the hydrogen atom in its ground state, I get a 3-fold degenerate level, okay, which is atom energy plus A by 2, and I get a 1-fold degenerate level, non-degenerate level, which is atom energy minus 3A by 2, and this energy separation is 2A. Okay. So this is what the hyperfine interaction is telling us. Now this energy separation for hydrogen is of the order of 5 microelectron volts. Typical energies in the hydrogen atom are tens of electron volts, and fine interactions are of the order of electron volts. So these are much smaller than the fine interactions. These are order alpha squared smaller, where alpha is the fine structure constant. So these are much smaller than the fine interactions, just 5 microelectron volts. And if you convert this into wavelength, it's about 21 centimeters, which is in the microwave regime. So if you have hydrogen gas in the atmosphere, in the universe, and you have a radio telescope that is tuned to picking up wavelengths of 21 centimeter, you can look at the concentration of hydrogen around the universe. Okay? And by Doppler shift of this wavelength, you can see whether the universe is expanding or contracting. In fact, this hyperfine interaction was used in making a microwave map of the universe using a satellite called COBE, C-O-B-E. And it helped us understand that the universe is expanding, because this frequency this wavelength was redshifted, which means that the universe was receding away from us. So this frequency, this wavelength of 21 centimeter, which also corresponds to about 14 megahertz, is one of the precisely measured, experimentally precisely measured values in all of physics. Okay, in all of physics. So its precision is 1 into 10 to the power 13. So it's been measured with a very precise, a really precise value. And theory is only precise as far as the hyperfine interaction is concerned up to 10 to the power 6. So the experiments have measured this frequency with astounding precision. Okay. So this is the origin of the hyperfine interaction. It's the energy scales in hyperfine interaction for the hydrogen atom are really small. But if you have quark anti-quark binding, the energies can be really large. They can be of the order of mega electron volts. So if you have a quark, an up and a down quark, they can form bimesons, and the interaction corresponding in hyperfine interactions for quarks and antiquarks can be really, really large. Okay, so this gives you an overview of the hyperfine interaction, and this uses the machinery of the two-particle spin-half systems that we do. But there is more to it. I started off with the premise that I would like to add angular momentum. So once we've defined the basis states for the four-dimensional Hilbert space, we've defined hyperfine interactions, we would now like to move to see how all of this connects with the addition of angular momentum. we have these two spin half systems. Let's define a total spin angular momentum S. Okay. So this is, since this is the only angular momentum I'm talking about, I don't have to worry about the orbital angle. Okay. So it's just S. So this S is really S1 plus S2. Okay, I define S. This is how I define S. It also means that S1x plus S2x gives me Sx. Okay? S is the total spin of this composite system, of this bipartite system. S1 is the spin of the proton, S2 the spin of the electron. But now we have a bipartite system and we want to find out the angular momentum, spin quantum numbers and the azimuthal quantum numbers of the total system. Okay? Likewise, we can have S1y plus S2y, and this just gives me the y component of the total spin. Now I'm going to add up the spins of the component systems to give the total spin of the bipartite system. Okay. And I have S1z plus S2z to give me SZ. Okay. And remember that when I'm talking about a composite bipartite system, when I write S1, is it a 2x2 matrix or a 4x4 matrix? When I just write S1, it's a 2x2. Okay, but this is a 2x2 matrix, and 2x2 matrix, this adds up to give me a 4x2. No, S1 really is a shorthand for S1 tensored with the identity. Okay, remember this. And S2 is really a shorthand for identity tensored with S2. Okay? So these are shorthands. So you have to look at the context of what is the meaning of S1 and what is the meaning of S2. Okay? ये बात है. If I have S, okay, the total angular momentum, and I would like to find eigenstates of S squared. If S is an angular momentum operator, what is an angular momentum operator? An angular momentum operator is something that satisfies the commutation relationship given by the following. If we have an operator whose three Cartesian components follow this commutation relationship, it's called an angular momentum operator. And these angular momentum operators are generators of rotations. We've learned this in quantum mechanics. Okay? Now what we have is that if we have eigenstates of S squared, well, now what is S squared? S squared is simply Sx squared plus Sy squared plus Sz squared. Remember this. Correct? And this is also equal to S1 plus S2 whole squared. Okay, and this is equal to S1 squared plus S2 squared plus 2 times S1 dotted with S2. Right? So all of this is S squared. This is S squared, this is S squared, this is S squared. Okay. Now could you tell me why am I able to make this simplification? Why can I expand this square into this form? Why don't I write S1 dotted with S2 plus S2 dotted with S1? Because S1 commutes with S2. Okay, that's why I can make the simplification. Okay. Now I would like to find eigenstates of S squared. This is my total angular momentum. Okay. So we know that whenever we have an angular momentum operator, J, L, S, we can find joint eigenstates of the square of the operator and its component of any one axis, which we call the Z axis. So we can find joint eigenstates of S squared and SZ. In other words, S square commutes, since S square commutes with SZ, we can find joint eigenstates. Okay? Now the joint eigenstates, let's label those by S semicolon MS. Okay, now I'm using a semicolon so that you don't confuse it with the product states that I've written here. Okay? So the joint eigenstates of S square and SZ are denoted by S semicolon MS. Now, this is the total spin quantum number, the total angular momentum, the total spin quantum number. Okay? As yet, you don't know what its value is. Okay? And this is the azimuthal component of the total spin. So these are the joint eigenstates of S square and SZ. And how are they defined? They define in the following way, that if S square acts on S semicolon and S, what do I get? I get H bar squared S plus 1 S ms. And if SZ acts on S ms, I get H bar ms S semicolon ms. Correct? Alright. Now what I would like to find out these joint eigenstates of, what are these eigenstates? I would like to find those out. So now these states must also live in the 4-dimensional Hilbert space. Correct? So these states must also be representable in, for example, this basis, right? This is a choice of a basis. I should be able to represent these eigenstates of the total spin quantum numbers in this basis. Or in any basis. I can choose this basis as my starting point. Okay, is all of this clear? So how do I express these states as superposition of the basis states which span the Hilbert space? Okay. And what are the possible values of S? Because if I know the possible values of S, the possible values of MS are really clear. MS will span from S, S minus 1, S minus 2, all the way up to minus S. So there will be 2S plus 1 possibilities for MS. Okay, this is something we learned in Movement 1. So we need to know the possible values of S given two spin half systems which are combining to form a commutation system. Okay? ठीक है? अब हमने इस SMS, इस total spin state को जिसे हम U represent करें, we would like to find out how does it span out in the Hilbert space. In other words, how can it be decomposed into suitable bases? The basis that we choose is the direct product basis or the Zeeman basis that I've written over there. Okay. So, alright, so first of all, I would like to recap what are the basis states of S1 dotted with S2. 2 times S1 dotted with S2. These basis states are simply these states. Okay. Because the Hamiltonian is proportional to S1 dotted with S2. So the basis states, the eigenstates of this Hamiltonian are simply these states. Okay. So ket Z is one eigenstate of 2 times S1 dot S2. Right? This is one of these. The other is z minus z minus z, right? The third one is z minus z plus minus z over under root 2. Okay? And the fourth one is minus z minus z over under root 2. Now these are the four eigenstates of 2s1 up to s. Right? This is what we found here. Correct? That's the answer. Okay. I would like to, for simplicity, I would like to label these states differently. I would like to call this state T1, T subscript 1, for reasons that become clear later. I would like to call this state T minus 1. I would like to call this state T0. I would like to call this state S0. The T stands for triplet. This is a three-fold degenerate state for a Hamiltonian that is proportional to S1 dot S2. And this is called a singlet state. And there are three kinds of triplets and one kind of singlet. Okay? Now my S squared, I would like to find eigenstates of S squared. My S squared is given by this. S1 squared plus S2 squared plus 2S1 dot S2. Okay. First of all, I would like okay. Now is T1 an eigenstate of 2s1 dot s2? Yes, it is. Okay. What's the corresponding eigenvalue? Let's find that out. Okay. In fact, we already found it. If the Hamiltonian has a 2a over h bar square, then this eigenvalue is a by 2. Okay. So if 2s1 dot s2 acts on t1, I will simply get h bar square by 2 t1. Okay. If 2s1 dotted with s2 acts on t minus 1, I will still get h bar square over 2t minus 1. If it acts on t naught, it's again an eigenstate. I will get h bar square over 2t naught. Okay. Correct? We know that these are eigenstates of S1 dotted with S2 with the proper eigenvalues. We've already found out those eigenvalues. These eigenvalues are a by 2, but these are for the Hamiltonian. We multiply by the corresponding multiplying factor to get rid of these. We just get rid of these terms, 2a over h bar square. Okay? ये समझ आया कि मैंने eigenvalue डायरेक्टली कैसे लिखी? ठीक है ना? क्योंकि Hamiltonian की eigenvalue थी. The Hamiltonian was just a over h bar square times this. ठीक है? तो इन eigenvalues को मैंने correspondingly multiply कर दिया. Okay. By h bar square over 4a. ठीक है? Now if I take 2s1 dotted with s2, I know that the singlet state s naught is also an eigenstate of this Hamiltonian, okay, of this operator, and the eigenvalue will be minus 3h bar square over 2 s naught. Okay, this is a 3 by 2 file. So these are the 4 eigenstates of S1 dot S2. But our S square is really 2S1 dot S2 plus S1 square plus S2 square. Okay. Now let's see what happens when S1 squared acts on these states. When S1 squared acts on T1, T minus 1, T0, S0, what do I get? Now when S1 squared acts on this state, I get H bar squared. This S is half. Half plus 1 is 3 by 2. 3 by 2 into 1 half, 3 by 4 H bar squared. So I get 3 by 4 H bar squared T1. Okay. For this I get 3 by 4 H bar squared T minus 1. Let's see what I get for this. X. Sorry? Okay. What happens when S1 square acts on this? When S1 square acts on this, I get 3 by 4 H bar square. From here I get 3 by 4 H bar square. Okay. इसको देख सकते हैं S1 square acting on T naught. S1 square acting on T naught. What is T naught? 1 over under root 2 get 0 minus Z plus minus Z Z. Okay, I get 1 over under root 2. S1 squared acting on this gives me H bar squared half into half plus 1, which is 3 by 2. S into S plus 1, just the first thing. Z minus Z. Okay. Plus half 3 by 2 minus Z Z. So this is simply 3 by 4 H bar squared T naught. Okay? So I get 3 by, when S1 squared acts on T naught, I once again get a 3 by 4 H bar squared T naught. Okay, and when this S1 squared acts on S naught, I think I just get 3 by 4 H bar squared S naught T. Okay, because the only difference is now here I have a minus sign. If I have a minus sign here, I have a minus sign here, nothing else changes. Okay? So, sorry? 3 over 2? क्योंकि अगर यहाँ पे मेरे पास S1 स्क्वायर हो तो मैं यहाँ पे S1 into S1 plus 1. अगर यहाँ पे 2 होता S2 स्क्वायर तो फर्क तो नहीं पड़ता इनमें से किसी रिजल्ट.
रूट 2 कैसे हटा मुझे इसमें?
सॉरी,
रूट 2 कहाँ से कैंसिल हुआ?
सॉरी,
रूट 2 किससे कैंसिल हुआ?
ये वाला रूट 2
यस सर।
यहाँ पे कैसे आया?
नहीं, कैंसिल कहाँ से हुआ?
कैंसिल नहीं होता, ये यहाँ पे आया और ये डेफिनेशन है क्या, जी प्लस माइनस जी माइनस प्लस माइनस जी ओवर रूट
से
ठीक है,
ओवर रूट 2।
now let's see what we have here. We have this s squared, this is my s squared, s1 squared plus s2 squared. Now s, in other words, we found out that the four states t naught, t1, t minus 1, s naught, which are eigenstates of s1 or s2, are also eigenstates of s1 squared. They are also eigenstates of s2 squared. Okay, so they must also be eigenstates of s squared. In other words, s squared commutes with s1 squared, s squared commutes with s2 squared, s squared commutes with s1, s2, and all four of them mutually commute. So the four basis states that we found are actually joint eigenstates of all of these states. Okay. So what does this mean? Let's choose. So what we've established is that the major result is that the states which we've labeled as T1, T naught, T minus 1, S naught, they are joint eigenstates of s squared and sc, because these are eigenstates of s1 dot s2, they are eigenstates of s1 squared and s2 squared, so they must be eigenstates of s squared, and if they are eigenstates of s squared, they must be eigenstates of sc, because these two mutually commute. So this is the major result that we established. However, what we haven't established is what is the value of s. We have s squared and it acts on T1. Okay, let's find out what's happening here. So s squared acting on T1 really means s squared acting on z, the direct product of z with z. Okay. Now when s squared acts on that z, when s1 squared acts, I get 3 over 4 h bar squared. So I have h bar squared 3 by 4. When s2 squared acts, I also get 3 over 4. And when s1 dot 2 times s1 dot with s2, I get h bar squared over 2. So I get 1 half T1. Okay. Now what is this? This is 6 by 4 plus 8 by 4, which is 2 h bar squared T1. Now if I compare this expression with this expression, what is the value of s for this, for T1? What does this T1 really mean? This means that for this state, s, the total quantum number is 1. Okay. We also want to find out what's the corresponding value of ms. So if I have sz acting on T1, which really means sz acting on zz, I get h bar squared over 4 zz. Is that correct? Sorry. acting on Z plus S2Z acting on Z. This gives me H bar over 2 plus H bar over 2 at Z H bar. Now if I compare this expression with this expression, what's the value of MS? 1. Hence, what this really means is that this state T1, which really is ket Z, which is the direct product Z, is also an eigenstate of S square, of the total spin quantum number. And this state can also be written as S equals 1, MS equals 1. Okay. Likewise, T naught, which is really 1 over under root 2 Z minus Z plus minus Z. If you work out this, if you start instead of with T1, you start with T0, you can prove that this corresponds to a total spin quantum number of S1 but with an azimuthal quantum number of 0. Okay. By the way, is this an entangled state? Yeah. Is it a pure state? Yes. It's a pure entangled state. Okay. If I take the state T minus 1, which is 1 over under 2 Z minus Z minus Z, this would correspond to S equals 1 and S equals minus 1. So all three of these states are quantum states with a total spin quantum number of plus 1.
This one should be minus Z only.
Okay. So these three states are eigenstates of the total spin quantum number. They have a spin angular momentum of plus 1. So if you look at the joint system, this joint system, if you look at the electron and the proton together, this joint system, if it is in one of these states, it has a total spin quantum number of plus 1. Likewise, if you take S naught and exactly repeat the same procedure that we've done here, this would correspond to 1 over under root 2 ket Z minus Z minus Z ket Z. This will correspond to S equals 0. A spin 0 quantum state. Now you have two spin half particles, you look at the total angular momentum, it can be plus 1 or 0. And this, if S is equal to 0, MS has to be equal to 0. You will notice that all four of these states are mutually orthogonal. They also form a basis. They are joint eigenstates of S square and SC. They represent these states are called the total angular momentum states or total spin states. You have started off with two spin half particles. S1 was half, S2 was half. If you want to calculate the total spin S, the two possible values of S are given by S1 plus S2 and S1 minus S2 for us. So this is 1 and 0. And corresponding to each value of S, we have 2S plus 1 values of MS. Okay. So these four states are the eigenstates of S squared and SC. They are joint eigenstates of S squared and SC. These are called the triplet states. These are spin 1 quantum states, and this is spin 0 quantum state. Okay. Now we look at more applications of this concept in our next lecture. We also have to do a makeup lecture which we will do next week. And we generalize this statement of adding up arbitrary angular momentum. What if we have a deuterium atom in which instead of a proton inside the nucleus, you have a proton and a neutron. The proton and the neutron are both spin half particles. So they will combine to give a total nuclear spin of 1 or 0. Now there is an electron outside. Now that electron is interacting with the spin 1 particle or with the spin 0 particle. Okay, so how do we generalize this scheme of addition of angular momentum, and what are the corresponding eigenstates? Okay, and how do these states evolve in time when this quantum system of an electron and a proton, or a hyperfine interacting coupled system, a two-body system placed inside a magnetic field? How does the state evolve? What happens to the singlet? What happens? Does it go to the triplet and so on? Alright, so we'll inshallah meet on Monday. I'm preparing